all yours.
All right. Hi, everyone. So my name is Siddartha Devic, and I'm going to be presenting some work today, which is a joint work with Alexandra Korolova, who's at Princeton, and David Kempe and Vatsal Shran, all three of us who are at University of Southern California. So the work that we're going to be talking today is called Stability and Multigroup Fairness in Ranking with Uncertain Predictions. Okay, let's get started. So the motivation here is really these sort of score-based ranking systems. So the sort of motivating example I'm going to talk about throughout is yesterday I just went on my LinkedIn account and I searched machine learning developer, right? And so uh, like these are the actual responses that I got on LinkedIn. And so I have like these people that I'm, second or third connected with, and they are ranked in some order, and maybe also some jobs come up as well. So the question, is like, how does LinkedIn actually get to the point? So when I put in a search query, I'm going to get a ranking of jobs and maybe a ranking of people as well. And I think it's an interesting question. So, the first step is like when I search up machine learning developer, LinkedIn has some set of candidates which are, maybe my second hop or third hop connections. And so like here, the candidates are going to be Junyoung, Ikechukwu, and Samin. And it feeds all of these candidates into like a relevant score predictor, right? So this is just going to be a function from candidates to 0, 1. And it's sort of, you should think of as like a black box classifier, which is trying to predict the probability that each of these individuals are actually relevant to the search query, right? So maybe it predicts the score between 0 and 1, which corresponds to the probability that any of these individuals are actually relevant. And once it has these scores, how do we then produce the ranking? Well, typically what we do is we actually just rank by decreasing relevance score. So here, maybe Samin had the highest relevance score, 0.99, so they will go into the top position on the ranking, and then Junyoung and then Ikechukwu, right? So this is sort of the standard way that some ranking systems are built. I think so. Brian Su at LinkedIn gave a talk earlier in the semester here, and I think they actually use something like that at LinkedIn. But this is not how all ranking systems work. Sometimes there are these learn to rank uh, schemes where you just output the ranking directly instead of first going through a score, right? But in this talk, we're going to be focusing on these score-based ranking systems where you have some predictor which first generates a score and then you rank by decreasing relevance score. Okay. And so the motivation for us is actually this step here. So we're going to like assume that these predictions are given to us, and we're going to think about, this rank by decreasing relevance score portion of the system. So first of all, this is definitely a normative decision that you can make. How do you actually turn these scores into the ranking? How do you turn these predictions into the ranking? Right. So, ranking by decreasing relevance scores may be one approach, but we're going to argue that maybe you might not want to use that approach in all settings. And maybe there's some particular reasons that um, uh, ranking only by decreasing relevance score isn't really sort of it gives us the right properties that we want. And so to sort of motivate that a little bit, let's consider a setting where maybe we have a small variation in the predictions for some individuals. Okay. So, previously Junyoung had a prediction of 0.98. And now we're going to say, okay, what if his prediction was actually 0.99, which is something very close to 0.98? And similarly, Samin had 0.99, and let's say he has 0.98 now, right? So we've injected a little bit of maybe noise or randomness from the training of this classifier. And somehow the predictions have sort of slightly changed. And now if we rank by decreasing relevant score, notice that we actually will put Junyoung first, and then Samin, and then Ikechukwu. right? So somehow this small amount of noise, which is it's not even obvious whether this amount of noise is actually meaningful. Like what is the quantitative meaning between a 0.99 and 0.98 prediction? Well, that small amount of noise has actually completely shifted the order of the ranking. And this can be pretty consequential if we're looking at sort of queries by recruiters, and maybe recruiters are only taking the top one or two candidates for any query. Well, somehow there was somewhat of an arbitrary choice made here between Junyoung and Samin, right? Even though they're basically equally qualified because their scores are so close to each other, one is deterministically placed above the other, and it seems like, you know, not the best in the case of these like predictions that I'm giving here. Okay, so that's brings us to our first sort of outcome that we're focused on, and that is going to be stability of rankings, right? So somehow this deterministic ranking, which ranks by decreasing relevant score, is not very stable in terms of small variations in the predictions given as inputs, right? These small variations can introduce these large changes in the finalized ranking. And so that's something we want to think about preventing. So that by itself is, you know, maybe the sort of motivation for studying this work and studying this process. So stability was sort of our first motivation, but we'll see that actually by, you know, thinking about other ways to turn predictions into rankings, in particular, maybe by not doing this decreasing by relevant score aspect, we'll see that maybe actually there's some other nice properties that we can preserve, not only stability. So you know, yeah, so for example, one of them is going to be considering whether we can actually consider uncertainty in the predictions, which it's not clear that these ranking by decreasing relevant score will actually do. Okay, so that's sort of the motivation set up for the rest of the talk. So now I'm just going to define some sort of formal notions. Um, our first notion is going to be that of a probabilistic or uncertainty aware predictors, right? So uncertainty is sort of a well studied concept in classification. Um, so I'm going to introduce some notation here. So I'm going to say delta L is going to be the L-dimensional probability simplex, right? So this is just a set of all distributions over L labels. And we actually have many predictors of the following form, you know, that map individuals to some distribution over predictions, right? So maybe we can think about some particular settings. So think about this setting of loan repayment prediction. So a bank might try to have a predictor F, which predicts the probability that a certain individual X will repay a loan, or the probability that they do not repay the loan, right? So that this is going to be a vector in delta 2, right? You can really just, yeah. And so another example might be this sort of criminal recidivism prediction example, another delta 2 classifier. So we might say that the predictor is trying to predict the probability that X commits a crime if released on bail. And more generally, we can think of any multi-class classification problem, let's say like with learned by a neural network with a softmax layer, right? So if we have a softmax layer, we're actually going to be getting this like distribution over the classes. And since we are working with ranking, we're going to need this little assumption here that basically is saying that there's a strict ordering on the classes. So class L is going to be more valuable to the candidate than class L minus 1, which is more valuable all the way to class 1. So let's consider this, you know, the last example I have is with the LinkedIn classifier. So let's say LinkedIn had a classifier that predicted whether candidates applying for a certain job were relevant, neutral, or irrelevant, right? So this classifier would predict a distribution over all these three classes, but clearly every candidate wants to be relevant for a job, and they would prefer to be relevant over neutral, and they'd prefer to be neutral over irrelevant. So this is called, you know, this is maybe known as this ordinal regression setting. ordinal classification setting. But we don't really talk about it too much. All we're saying is that the labels themselves have a strict ordering over them, and the predictors are outputting these distributions over the labels. Okay. All right. So these are probabilistic predictors or randomized predictors. They go by many names. Okay, and to formally define a sort of ranking, we're going to talk about ranking distributions. So the input to a ranking is going to be n individuals always. And a ranking distribution might look like the following. So it might say that, with some probability, let's say 60%, in this setting, we have Alice, Bob, and Charlie, right? So with some probability, Alice gets ranked in the top place, Bob gets ranked in the second place, and Charlie gets ranked last, okay? And with, let's say, 30% probability, Bob gets ranked first, then Alice gets ranked second, and Charlie gets ranked last, right? And then with the final 10% amount of probability, Charlie, then Bob, then Alice. So this is like a ranking distribution, right? So we have 3 different rankings, which each take place with some probability. So to sample from this ranking distribution, you could first sample a number uniformly between 0 and 1, and then pick the corresponding ranking. And that's somehow an unbiased way to sample from this ranking distribution. And notice that randomness is key here. We could always just output only one of these rankings deterministically if we wanted, but randomness will turn out to be useful for achieving some of the notions that we require. And that's sort of standard in the ranking literature. And just a small technical detail, if we want to output these ranking distributions, it turns out to be sufficient to only think about these certain matrices, which are known as doubly stochastic matrices, right? So a doubly stochastic matrix is just a matrix where every row and column is between 0 and 1, and every row and column sums to 1, right? So every entry of the matrix is between 0 and 1, and every row and column sums to 1. And it turns out that every doubly stochastic matrix corresponds to a certain ranking distribution, right? So this is not an obvious fact at first glance, but it turns out to be sort of standard in the ranking literature. To see how we can derive the corresponding doubly stochastic matrix for this output, just consider each of these rows here as one of these permutation matrices. So 60% probability, Alice gets ranked first, then Bob, then Charlie, right? So if we consider the first row is Alice, the second row is Bob, and the third is Charlie, and each of the columns are a certain rank that, rank 1, 2, 3, right? The second matrix here is going to be Alice obtains rank 2, so she gets a 1 here in the middle, and then Bob gets rank 1, and Charlie gets rank 3, etc. So this turns out to be a convex combination of these permutation matrices, which will always be a doubly stochastic matrix. And like I said before, every doubly stochastic matrix induces a ranking distribution, and this is a theorem of Birkhoff von Neumann. And it's sort of standard in the ranking literature. So we should really think about rankings as being doubly stochastic matrices. So they're in our head, these two things are the same object. So that's sort of the as a small technical part of our paper is that rankings are equivalent to these doubly stochastic matrices. I guess one thing also to notice, the final thing to notice here, is that doubly stochastic matrices also capture deterministic rankings. So if there was no probabilities here and all of the probability mass was on one of these rankings, a deterministic ranking, that itself would be one of these permutation matrices, and that permutation matrix is a doubly stochastic ranking, or a doubly stochastic matrix, right? So if you think about any of these 3 permutation matrices, that is a doubly stochastic matrix. So doubly stochastic matrices are enough to capture both deterministic and randomized rankings. Okay. And anyone in the audience, feel free to interrupt me if you have any questions. I don't want to be going too fast.
No,
All
all
right,
good.
great. Okay. So now we have these two objects, right? We have these uncertain predictors, and we have our W stochastic matrices, which are really just ranking distributions. So now we're ready to, define what we mean by a ranking function itself. So first, this bold P, we're going to say that this is a set of all n by L prediction matrices. So what is a prediction matrix? So a prediction matrix is just going to be a matrix with n rows and L columns, where every row of the matrix corresponds to the prediction of some classifier on some input, right? So if we're given, x1 through xn, n data points, and some classifier f, we can construct the corresponding prediction matrix by putting f of xi at every row in this matrix, right? So notice that because of our uncertain, our sort of like probabilistic predictors, every row is going to be a distribution over the L labels, right? And we have n individuals, so we're going to have n rows. Okay, and so notice that, I guess the only thing to notice that like every row sums to 1 because every row is a distribution. Every column doesn't necessarily sum to 1. Okay. All right, so this is what a prediction matrix looks like, and they're going to be sort of central objects. And finally, this bold M ds, that's just going to be the set of all n by n doubly stochastic matrices, right? So the set of all matrices where, the rows and columns sum to 1 and the entries are between 0 and 1. Okay, so now we're ready to define our notion of a ranking function. So a ranking function is any map which maps from the set of all prediction matrices to the set of all doubly stochastic matrices. Right. So all it's saying is that you give me n predictions, in some arbitrary order, and I'm going to give you a ranking distribution. Right. So in particular, notice that this definition captures our previous example. So in our previous example, we had these probabilistic classifiers over 2 dimensions. We have 2 labels, right? The 2 labels here are going to be probability of relevance and probability of irrelevance. And so we can write each of these um, predictions as these like 2-dimensional vectors and feed them to a ranking function. And the rank by decreasing relevance score is actually a ranking function, right? So it takes in 3 of these predictions and outputs this deterministic ranking, or the utility optimal ranking, which just sorts these predictions by decreasing probability of being relevant. So that by itself is a ranking function, right? Hopefully that's clear. And yeah, so it's implicitly a ranking function. Like we've sort of defined explicitly here, um, like a formal definition of a ranking function, whereas, it's sort of obvious, it seems like the obvious thing to do is just to sort of sort these by decreasing score. But, it's definitely captured by this framework of ranking functions. Okay. So what are some desirable properties of ranking functions which we consider in our work? Well, the 3 desirable properties is first, stability, which we've already motivated in our introduction, right? Small variations in the predictions should not cause large variations in the output of the ranking function, right? Anonymity and fairness are going to be 2 additional properties that we will talk about. Fairness, has many definitions, but we'll show that sometimes stability can imply some nice fairness definitions. Okay, so our next order of business is to sort of formally define what we mean by stability of a ranking function, now that we have these objects called ranking functions. What are some other motivations for stability? So I told you, like, small amounts of noise in the inputs should not cause large changes in the outputs. Well, why should we even be stable to small amounts of noise in the inputs? Well, it turns out, right, that ML training algorithms are often themselves sensitive to randomness or noise during the training process. So if I train 2 different neural networks with different initialized weights, the outputs for certain individuals might have like small perturbations, right? Or they might look completely different. But we're thinking about the case where maybe due to randomness in the initialization, Ikechukwu or Samin gets somewhat of a different prediction, like a small change in the prediction versus if the weights were initialized a different way, right? So somehow we shouldn't penalize the candidates who are applying for a job based on how the neural network used to classify them was initialized. Like that seems very arbitrary, right? So that's sort of what we're trying to do here with stability is we would like ranking functions to be agnostic to these small amounts of noise in the input predictions. And this works to sort of reduce this new notion of like arbitrariness in the predictions or arbitrariness in downstream tasks, right? This is somewhat of an arbitrary decision that you're putting one candidate in front of another if there's only like a 0.001 difference in their prediction. And I encourage you to check out this Cooper et al. Paper, which is very nice. Okay, so now we're ready to formally define the stability of a ranking function. Hopefully it's well motivated by now. So we have a ranking function, and we're going to say that this ranking function is gamma stable if for all prediction matrices P and P prime, right? So if you give me a pair of any two prediction matrices, the following holds true. So all I'm saying here is that the outcome of the ranking here on the left-hand side, between like the difference in the outcome and the ranking on the left-hand side, is going to be bounded by gamma times the difference in one norm in the predictions. Okay, and so what do I exactly mean here on the left-hand side, difference in the outcome of the ranking? Like, what is this infinity norm? All I'm saying is that this infinity norm is just going to be the maximum entry, right? So the maximum difference across all of these individuals and ranks 1 through k, right? So the output of ranking is a n by n matrix, which corresponds to every position corresponds to what is the probability that that individual will obtain a certain rank. So the difference in that probability for every individual and for every rank is going to be at most gamma times the one norm difference in predictions. So it's sort of like a quite natural, intuitive notion of stability. All we're asking for is that, a certain individual, their probability of getting any particular rank doesn't change too much if their input prediction like maybe has a small amount of noise, right? We're saying that it changed only by a factor of gamma. So, this is really like simply just a Lipschitz condition, right? So the difference in the ranking output by R is going to be bounded by the difference in the inputs. So this is a notion of stability which we propose. I think it's quite natural. If you have any questions about like the norms or something, we can talk about that later. But yeah, I think it's quite natural. Okay, so we'll need one more key tool here before we talk about some of the implications of this stability definition. So in particular, we're going to think about anonymity as another condition we might be interested in. So what is anonymity? It says that your identity should not matter when ranking you, only your prediction. Like only your, relevant score or anything should matter when ranking you. And how do we formalize this? Well, it's pretty simple. We just say that if we apply a permutation to the rows of the prediction matrix, then a ranking function which is anonymous should have the same permutation applied to the output in the ranking distribution, right? So what does this mean? It says that like really a ranking function which is anonymous treats the input as a set rather than an ordered matrix, right? It's just saying that we really don't care about whether individual one was put first in the ranking in the predictions or last in the predictions. It's just saying that we should only care about the value of the predictions and not like sort of where they lie in the matrix. This is definitely a normative decision, but we think it's a reasonable one to ensure. Right. So all it's saying is that like we should treat the predictions as set rather than as sort of ordered input. Yeah. output of the ranking function should not change if you change the order that the predictions are given to it in. So it's another like somewhat natural condition. Okay. And it turns out like it's very easy to come up with ranking functions which satisfy um, this this anonymity condition. Coming up with one that satisfies the stability condition is maybe less obvious, but you might be able to guess. Okay, so our first little result is that if we have a stable and anonymous ranking function, excuse me, if we have a stable and anonymous ranking function, it will compose well with individually fair predictors, right? So what is an individually fair predictor? A probabilistic predictor F is, let's say, beta D individually fair with respect to some distance metric D if the output predictions are close in one norm by beta times D of x and x prime, right? So basically, this is saying that similar individuals in terms of a similarity metric D between individuals, similar individuals will have similar predictions. You know, it's a sort of a very basic definition. I think I should put here that proposed by Dwork et al. 2012, sort of a seminal result in the fairness literature. And really, this is a nice little Lipschitz condition on the predictor F. That's all it is. And recall our gamma stability notion. So notice that these two definitions in their statement, they both look like Lipschitz conditions. They're both kind of natural. And so it turns out that we can combine them nicely. So our first proposition is saying that if I have a stable and anonymous ranking function, it's going to compose well with an individually fair predictor. So if I fill my prediction matrix P with predictions from this individually fair predictor, then I can actually inherit some of these individual fairness properties in my output ranking. In particular, the ranking output for X is going to be, for any pair of individuals, X and X prime, their ranking output is going to be close in terms of beta, gamma, and this distance metric, right? So it's saying really that individual fairness is preserved for stable ranking functions. And the proof is not so hard. Really, you should think of both of these definitions above as being Lipschitz conditions. And it turns out that, Lipschitz conditions compose nicely with Lipschitz conditions. So it's not a very surprising result, but we've already derived something maybe non-trivial from using this stable and anonymity condition of our ranking function. Okay. All right. So, maybe the question which I'll have time to answer is, can we actually achieve stability? Well, first of all, I think the motivation for this setup was that this deterministic ranking function, which always orders Samin in front of Junyang, isn't actually, going to be stable because small variations in the input predictions are going to flip the order of the ranking completely. We can say something more like slightly more general. So we can say that every non-trivial deterministic ranking function cannot be stable. And the proof is exactly as before, right? So if we have Samin and Junyang, with their scores that are close to each other with this set of scores, Samin will be first. If we have another predictor G where Junyang has a slightly higher score, with this set of scores, Junyang will always be first. And we can take this difference between F and G to be epsilon and shrink epsilon arbitrarily small. And you get that basically we get a flip which violates the stability condition. Okay. So all we're saying is that like G and F can be taken arbitrarily close to each other, but they can still induce a flip in the output. And so, the very natural next question is like, if we can't use deterministic ranking functions, does there exist some non-trivial stable ranking function? Right. So we're going to argue that there does. And the function we're going to talk about is what we call this uncertainty-aware ranking function, which was actually proposed in some prior work. So what is this uncertainty-aware ranking function? I'm going to give a little bit of an example. So let's say that in the present, we had these two distributions for Alice and Bob, distributions over the relevant and irrelevant classes. So in this picture, let's say that Alice was actually better than Bob with probability 80%, right? So Alice is going to be more relevant than Bob with probability 80% if we were to sample from these two distributions. So what does that actually mean? Well, it means if we put on our Doctor Strange hat and look at all possible future worlds, right? In 4 out of the 5 of these future worlds, and 80% of these future worlds, Alice is going to be the one that's more qualified for the job. Whereas maybe in 1 of the 5 of these future worlds, Bob is the one who's more qualified for the job. So Ashdeep Singh, David Kempe, and Thorsten Wakims in 2021, they sort of proposed this very natural selection criteria. So what they say is that, this uncertainty aware ranking function, it just says that the probability that we should select Alice in the present should be at least the probability that Alice is more qualified in the possible futures. So that's 80% of the time. And the probability that we should select Bob should also be at least the probability that Bob is more qualified, right? So that actually leads us directly to this like 80-20 selection rule, right? So hopefully that's somewhat intuitive. So all we're saying here is that we should use the uncertainty in the distribution that's given to us in order to make this selection. The first thing you might notice is that this is actually directly counter to the optimal, utility maximizing function, selection function here, which would always select Alice, right? If I wanted to select the person who is most relevant or most qualified with the highest probability, I would always just select Alice here. But what I'm saying, what I'm telling you to do is actually to select Alice with some probability and Bob with some non-zero probability. So it's directly counter to utility optimals. So there's somewhat of a trade-off here. Like I said, it's originally proposed for fairness and uncertainty. It's saying that we should respect the underlying uncertainty in the predictions in order to produce like a fair outcome downstream. And maybe a strength is actually that it's very natural and easy to explain. If you can explain it in one slide to someone, I think it's pretty reasonable. If we look at the merit and Alice has more merit than Bob with some probability, Alice should be selected with that probability. It takes a little bit of care to exactly apply this uncertainty aware ranking function to this multi-class classification setting, but we're just going to skip over that. That's sort of an uninteresting technical detail. And so our first result, like our first main theorem, is going to be that this uncertainty aware ranking is anonymous and also one stable. So the sort of intuition for this, which I'll get into in a second, is that by considering uncertainty in the predictions as they're given to us, you can sort of imagine that that the output is not going to change so much in terms of the randomized ranking, right? So here, if imagine that Alice had more merit than Bob with 0.79, and Bob had more merit than Alice with 0.21, well, the actual final selection criteria is going to look extremely similar, right? We're going to select Alice with probability 0.81 and Bob with 0.19, or sorry, the other way around. We'll select Alice with probability 0.79 instead of 0.80, and Bob with probability 0.21 instead of 0.20, right? So somehow, like a small variation in the input predictions here is still stable because we consider the randomness in those predictions, right? So I think it's quite intuitive why this is one stable. Yeah, I said concerning uncertainty turns out to be vital. We also we show that our analysis is tight. So we show that UA ranking is not gamma stable for gamma less than 1/2. So really the true gamma parameter for UA is between 1/2 and 1. I don't know if I can improve it from 1 to 1/2, but that's sort of like an uninteresting question. And proof intuitions, I'll say, is that like randomness is helpful for stability. And we've actually shown, like, there's been some previous work by some folks at Google which actually show this empirically. They show that when you're training learning to rank functions, ranking with some sort of randomness during training turns out to be very helpful for achieving some empirical notions of stability. But we're like, our work is the first to sort of give a theoretical foundation for this, to this very like nice intuition. And sort of we use this key lemma that says that, conditioned on individual I being of a certain class, we can bound the difference in outcomes between two different prediction matrices in terms of their total variation distance. So that's sort of the key insight. Okay. So yeah, so we have this like very nice stability result. It's quite intuitive, and UA ranking also itself seems to be intuitive. What else can we do, right? So stepping back now, like besides stability, is there any sort of other properties that we can derive? So we already showed that a stable ranking composes nicely with an individually fair predictor. Oh, I guess I also wanted to say that we also ran some simple experiments. So to check whether like our theory really holds up in practice for UA ranking. So what we did here is we trained some predictors, some neural networks on these different data sets in like two and three dimensional number of classes, and we applied this like score-based ranking function. So if you recall, in our definition of stability, this max norm here, the max norm in the difference of the output, should be bounded above by this one norm in the difference of the input, right? So P and P prime are two different prediction matrices generated by the neural networks that we train. And we actually see that it's the case. So UA ranking here is bounded way below the difference in the prediction matrices. Whereas here, this R-opt I've put here is this deterministic ranking, which puts Samin and then Junyoung and then Ikechukwu deterministically based on their predicted scores in decreasing order of relevance score. Right. So all this chart is saying is that like on average, not on average, but like for every instance, we did this 30 times on both of these data sets, and we found that like actually UA ranking is extremely stable in practice. Maybe in some average case sense, like you can even get better stability guarantees than the one we proved. So that's very nice. It shows that this very intuitive method is also nice in practice, and it's sort of a larger scale when we're operating with neural networks. Okay, yeah. So like I said, we already showed some results that said that stability composes nicely with these individually fair predictors. And so another way to state this is the following. Right? So if you give me some F star, which is actually the ground truth label distribution, and I have a predictor F, which is learned, right? So now we're working this setting where we assume that there's some ground truth F star. So this is somewhat of a classic setting and from the more perspective of like machine learning. If F is basically epsilon accurate everywhere, if F is like a very good approximation of F star, then any gamma stable ranking function guarantees that for every vector X, bold X of individuals, so if you give me n individuals and like a very good predictor, then essentially the output of my ranking will be very good. It'll be close to the output of the optimal ranking by a factor of gamma times n times epsilon, where n is the number of individuals, gamma is the stability of a ranking function, and epsilon tells us how good our learned predictor is relative to the ground truth. Right, so what is this saying? Well, it's saying that if we have accuracy in the predictor and stability of the ranking function, then the output ranking will be close to the output ranking of the ground truth predictor, right? So this is very nice. It's saying somehow that we're recovering the ground truth in terms of the downstream task of ranking if our predictor is good and our ranking function is stable, right? So notice that this doesn't hold for the utility optimal ranking. In fact, like it's the same example which I've given through the entire talk. If we take F and F star to be epsilon close, if we're coming to if our predictor is coming from the wrong direction, we can get arbitrarily close to the F star, but our ranking will still be totally flipped, right? So what do I mean exactly? Right, so if I predict 0.99 for Junyoung and the ground truth is 0.98, and I predict 0.98 for Samin and the ground truth is 0.99, well, the ground truth ranking is going to look like very different than my ranking if I'm ranking by decreasing relevance score. So this is not saying anything more than, stability. This is just basically applying stability with one of the prediction matrices being generated by the ground truth rather than like two different predictors. So it's not saying anything interesting. Excuse me. But in practice, we often, our predictors often do not achieve small error, right? So usually F star and F are not epsilon close over the entire domain because this turns out to be like this finding this, learning this Bayes optimal predictor F star turns out to be like a computationally and sometimes information theoretically challenging task. So, the question is there a looser condition than, being epsilon close or epsilon good everywhere that guarantees that we're still going to get some, accuracy guarantees on our downstream ranking? Right, so can we obtain guarantees on the resulting ranking even if the predictor doesn't have this um, error epsilon with respect to the ground truth? Well, we'll have to be slightly looser. So we can't, this result here is here on the left, we're saying that for every individual, their ranking will be good, right? So this max norm is just saying that the maximum difference between these two matrices over every individual in every position is going to be bounded by gamma times n times epsilon. And so, we can't hope to achieve something like this, but we can coarsen our guarantees and say that, okay, maybe we can say that like at the level of subgroups, we can also achieve good and accurate rankings, right? So maybe at the level of individuals, this is impossible, but maybe at the level of subgroups, we can hope to achieve something. Also, Rebecca, how long should I go for?
I mean, you're welcome to go for as long as you like. Like normally it's about an hour,
Okay.
but you're welcome to keep going.
Okay, great. Yeah, so I'll shoot for an hour. So yeah, so we'll need to coarsen our guarantees. So now we're going to talk about properties of our predictor F, which are uh, not exactly like epsilon accurate everywhere, but maybe easier to achieve. So, the first property, especially since we're utilizing uncertainty in the predictions to output the sort of ranking, it makes sense to think about calibration, right? So what is calibration of a predictor? Um, the calibration of a predictor is a property of a predictor. If we're given some ground truth F star and some distribution D, which is supported on the individuals, then it's saying that for every vector bold V in the delta L, um, essentially conditioned on um, uh, looking at all of our predictions where F predicts V, we're going to be close to the ground truth. So this is like a very mathematical definition. I think it's best visualized in 2 dimensions. So in 2 dimensions, all we're saying is uh, my confidence scores are meaningful, right? So all I'm saying is that if you look at all of the individuals for which I predict, let's say 0.6 at, then 60% of those individuals should actually have label 1, right? It's saying that when I predict 0.6, that 0.6 is very meaningful in a quantitative way. It's meaningful in the sense that 60% of those individuals should have the positive label, right? So it's very natural definition for 2 dimensions, but I've sort of defined it here for multiple dimensions. Similarly, if you look at all the individuals who I predict 0.1 for, 10% of those individuals should have um, class, 1. And the important thing to notice here is that this is with respect to some distribution. So we only need to be sort of good on average for like an individual sampled from this distribution. Yeah, and we have algorithms which turn predictors into calibrated predictors. like Platt scaling, and usually these come at basically very minimal loss in accuracy. Okay, so calibration is a very natural notion, but it's somehow too weak to give us guarantees at the level of subgroups, right? So if we want uncertainty estimates at the level of subgroups, maybe if we think about, ethnic minorities or something as being a subgroup of all of our entire population X, maybe our predictor is calibrated over the entire population, but still uncalibrated over like some particular subgroup. So this is the reason that, the literature has proposed this very natural notion called multi-calibration. So multi-calibration, all it is just saying that you need to be calibrated, not only over the entire population X, but also for some subgroup X, right? So here I just modified the definition by including a conditioning on the individual being in a certain subgroup S, right? So calibration not only over the whole distribution, but also on the conditional distribution um, given by D sub S, where we're trying to sample only from this particular subgroup, right? Okay, and just some final terminology here. So hopefully this notion is quite intuitive. So I say, like, if I have a collection bold C of subgroups S1 through Sn, and F is multi-calibrated for each of those groups in the collection, then I say that F is going to be C comma alpha multi-calibrated. Right? So if this multi-calibration condition holds not only for a single group, but like for a potentially complex overlapping collection of groups, right? So we're calibrated not only over the entire population, but also over this looking at subsets of the population. We're also calibrated there, and we're calibrated over all these subsets. And these subsets might be sort of overlapping or disjoint, or they can be arbitrary. And if we're multi-calibrated everywhere, we're saying that we're like bold C comma alpha multi-calibrated. F will be bold C comma alpha multi-calibrated. Alpha here is our sort of slack parameter. So it says we don't have to get exactly the right answer. We're just allowing some like amount of alpha slack. Okay. So this is a sort of a natural definition that generalizes calibration to also be some sort of group fairness metric. Okay. And it turns out that, it's definitely non-trivial, but I think it's a beautiful result that, we have algorithms for achieving multi-calibration at essentially no loss in prediction accuracy for certain collections of subgroup C. So these collections are, um, this is sort of outside the scope of this talk, but I definitely highly recommend this paper by Herbert Johnson et al. And also Parkshit Gopalan et al. In 2022. So there's definitely computationally efficient algorithms for achieving multi-calibration, which is not trivial, but very interesting in its own right. Okay, so I'll say that in practice, we can't, due to some sort of measurability issues, we can't achieve like perfect multi-calibration. So we actually need to think about bins over which we're multi-calibrated in, but this is maybe not so important. All right. So now this is sort of the second main result. So our first result was that UA rankings are stable, right? So we define some notion of stability and we say that these uncertainty-aware ranking functions are going to be stable. And now what I'm going to say is that these uncertainty-aware ranking functions also preserve some notion of multi-calibration. So what do I mean by that exactly? So you give me a distribution over individuals. So this is sort of a standard setup in machine learning. You give me some distribution over the domain, right? Which tells you like what the underlying population of individuals actually looks like. So I'm going to go through the theorem as follows. So if you give me a predictor, which is C alpha multi-calibrated, which means that it's calibrated not only overall, but also with respect to some collection of subgroups. And alpha is tells you what is the slack on the multi-calibration, what is the slack on the calibration for each subgroup. Then for every prediction bin, so I sort of glossed over this prediction bin thing, but it's not so important, right? So for every prediction bin, and then for every subgroup in my collection, and for every k in n. So k is going to be the rank that we're considering. So what is the rank in the final output ranking? Is going to be k from 1 to n. So this holds for every s and every k. We get some like very big scary equation that I'll like step through one at a time. Okay. So starting from the left, we're saying that we have an absolute value all the way on the output. And so we're saying that, okay, the first thing we're going to consider is this expectation term. So we're going to say in expectation over the randomness. So first we select n individuals at random from this distribution D. So we sample n individuals from this distribution that was given to us. And then I will be selected randomly from amongst these n individuals. Right, so what is this expectation? What is this randomness in the expectation over? It's saying there's randomness over first selecting n individuals to rank, and then selecting one individual from the n who we care about, right? So we're going to be thinking about the average outcome for a uniformly randomly selected individual amongst n, which are, randomly selected. Okay. And then the next two terms are indicator functions. So the first indicator function is going to be, okay, we're going to set the indicator to 1 if that individual we randomly selected belongs to a certain subgroup S, right? So we're saying that this holds for every subgroup S. So essentially, by conditioning that xi belong to S, we are essentially making it so that we're randomly sampling some individual from that group S, right? The second indicator function is sort of important only for this bidding kind of thing, which I'm going to ignore. So, right, so if we're conditioning here on this, essentially by putting this indicator vector, which checks whether xi belongs to this group S, we're essentially conditioning on sampling I instead of from all of the n individuals, we're conditioning on sampling I from being one of the individuals in that group S. So this is now saying like, essentially I've randomly selected one of the individuals from this particular group that I care about, right? So I first select n individuals randomly. Then I look at all the individuals who are in a particular group S, some particular subgroup S, and I select one of them at random. And for that randomly selected individual in my group S, the output has to be close from the output of our ranking function, UA, has to be close for if we were giving the ranking function the true predictions, F star, or we were giving our predictor F, right? So this bold arc IK says what is the probability that this randomly selected individual I from group K from group S is given position K, right? So because our ranking function like outputs these ranking distributions, if I give you if you give me an individual I can look at what is the probability that they actually achieve rank K. And so this sort of is the main term on the right here. This difference in probabilities is looking at what is the difference in the probability of that event I, or that event where I gets rank K. What is the difference in the probability of that happening if we were giving the ranking function the true F star, right? The true ground truth versus our predictor F. So sort of the key result here is that actually we can bound this quantity by L times N times alpha. So what does that mean? It means that, on average, if we randomly select individuals from each of these subgroups, then they're like the outcome on average for a randomly selected individual from the subgroup is going to be close to the ground truth, right? So it's somehow like a coarser guarantee than this um, uh, guarantee that I was talking about earlier, because we're only working at the level of groups. But this turns out to be computationally feasible to achieve because it's like possible to get F to be multi-calibrated, right? So here the key statement here is F only has to be multi-calibrated. It doesn't have to be accurate everywhere. So if F is multi-calibrated with respect to some ground truth F star, then we can guarantee, UA ranking guarantees that the outcomes, that sort of average outcomes for groups will be close together. And the closeness is going to be in terms of L, which is the number of labels, N, which is the number of individuals which we sample, right? And alpha, which is our slack parameter for multi-calibration. So alpha alpha is a parameter we can control because when we're turning a predictor into a multi-calibrated one, we can run an algorithm which depends on alpha. And it turns out that that algorithm is like computationally efficient to run for smaller alpha values. So yeah, so this is sort of our main result, and it's sort of saying that I just want to hit the point home is it's saying that like the average outcome for the subgroups will be close under our predictions F and the ground truth F star if F is multi-calibrated. Okay. Yeah, so this is sort of our main result. I have some other things, but I think I just want to summarize some of the key takeaways here. First, I want to say that stable ranking functions are achievable with randomness, right? If we output ranking distributions instead of just deterministic rankings, it seems like that these uncertainty-aware ranking functions of Singh et al. Are stable. The next sort of key point I want to mention is that by having ranking functions which are not just decreasing order by decreasing relevance score, we can actually derive some properties of, we can actually like preserve or inherit some properties of predictors in the induced ranking, right? So for example, we showed that if the ranking function is stable, we inherit individual fairness. And at the end, we showed that if for UA ranking, UA ranking itself actually inherits these multi-accuracy or multi-calibration guarantees from the predictors. So that by itself is like a somewhat surprising. We're not really defining new definitions of fairness in this work. We're just saying that there exist ranking functions which will actually preserve already existing notions of fairness from the actual predictors, which are used to generate inputs to the ranking functions. So, a nice like question is, are there other fairness properties which rankings can inherit, right? So if our predictor was maybe satisfied statistical parity or equalized odds, or maybe even some privacy guarantees, can we actually prove some results that the downstream ranking actually inherits some of these in some, a formal way? All right, so I think that's all I want to cover.